In this video, we consider the characteristics of power in circuits that have sinusoidal sources. All of the circuits that we examine are linear. That is, they contain some combination of independent sources, resistors, capacitors, and inductors. Any such circuit can be transformed into its Thevenin equivalent, like the one shown here. The circuit elements are labeled with phasor forms, so the source is V sub m at an angle of 0 degrees. The equivalent impedance of the circuit is Z, which is a complex number, R plus JX, where R, the real part, is the resistive part of the load, and X, the imaginary part, is the reactive part of the load. The impedance can be expressed in polar form as the absolute value of Z at an angle of theta. The phasor current, I, is the phasor voltage divided by the equivalent impedance, and that equals I sub m at an angle of minus theta. This is the general case where we don't know anything specific about the impedance. To help us understand the characteristics of power for the general case, it's instructive to examine power used by a purely resistive load, a purely inductive load, and a purely capacitive load. When the load is purely resistive, it means that the impedance is real, so its phase angle is 0. Because of this, if the voltage is V as a function of time equals V sub m cosine omega t, then I as a function of time is equal to I sub m cosine omega t. And the voltage and current are in phase as shown in the graph at the top right. The power used by the load is the product of the voltage and the current, and it can be written as V sub m, I sub m times 1 plus cosine of 2 omega t all over 2, and this is shown in the graph. Notice that the power is never negative. This means that energy is always flowing from the source to the load, where it is absorbed by the load and dissipated in the form of heat or perhaps light. Now let's consider the situation in which the load is purely inductive, that is, Z is equal to j omega L, where L is an inductance. We can write this in rectangular form, where we see that it's a purely imaginary positive number, or in polar form with magnitude omega L and phase angle 90 degrees. If the source is still V as a function of time equals V sub m cosine omega t, then the current is going to be I sub m cosine omega t minus 90 degrees, which is the same thing as I sub m sine of omega t. This means that the current lags the voltage by 90 degrees. The expression for the power simplifies to V sub m, I sub m sine of 2 omega t all over 2, which is shown in the graph on the lower right. Here we see that half of the time the power is positive, and during that time the source is delivering energy to the inductance. But inductors don't dissipate energy, they store it. During the part of each cycle that the power is negative, the inductance is sending energy back to the voltage source. Overall, the average power is 0. When the circuit load is purely capacitive, then the impedance is 1 over j omega c in rectangular coordinates, which is a purely imaginary negative number. In polar coordinates, it's 1 over omega c at an angle of minus 90 degrees. Again, when the voltage source is V of t is equal to V sub m cosine omega t, then the current is I of t is equal to I sub m cosine omega t plus 90 degrees, which is equal to minus I sub m sine omega t. This means that the current leads the voltage by 90 degrees. The expression for the power is the same as the one for the purely inductive load, except that there's a minus sign in front of this one. When the power is negative, energy flows into the capacitor and is stored there. and when the power is positive, energy flows from the capacitor back to the source. Overall, the average power is 0. In most circuits, the load is a mixture of resistive, capacitive, and inductive elements. In general, the current and power are not in phase but differ by theta radians. And the power is as shown here. We define capital P to mean the average power or real power, which is V sub n I sub m cosine theta all over 2. Notice that when theta is equal to 0, as it does for a purely resistive load, the cosine of 0 is equal to 1, and the real power is V sub m I sub m over 2. While when the load is purely inductive or purely capacitive, theta is either 90 degrees or minus 90 degrees, and the sine of both of these angles is 0. This confirms what we already know, that the real power used by both such loads is 0. We can rewrite P as V RMS I RMS cosine of theta. The RMS voltage and current are also called the effective voltage and current respectively. Cosine of theta is a special quantity. It's called the power factor. It's a measure of how in phase the voltage and current are with each other. The closer this angle is to 0, the more resistive the load is, and the greater the average power. Since it's cosine of theta, the power factor can be anything between -1 and 1, and is often expressed as a percentage between -100 and 100%. It's also common to state whether the current leads the voltage, which would indicate that the load is capacitive, or lags the voltage, which would mean that the load is inductive. When we wrote this expression for the voltage, we assumed that it was a cosine with 0 phase angle. However, it could have had a non-zero phase angle, which we would call theta sub v, and the current could have its own phase angle, which we would call theta sub I. We define the power angle to be the difference between these angles. In AC circuits, we know that energy flows in and out of inductors and capacitors. The instantaneous power in any such element can be very high, but the average power is 0. The peak instantaneous power associated with energy storage elements is called the reactive power, and it's denoted by the symbol Q. It's equal to V RMS I RMS times the sine of theta, where theta is the power angle. V RMS and I RMS are the effective voltage and current across the load. To emphasize that Q does not represent the flow of net energy, we usually use the units volt amperes reactive, VAR, instead of watts. Now let's define apparent power, which is the product of the effective voltage and current, with the units volt amperes or VA. We can use all these definitions to formulate a very useful equation. Let's add P squared to Q squared. When we do, we can substitute V RMS I RMS times the cosine of theta for P, and V RMS I RMS times the sine of theta for Q. We factor out V RMS I RMS squared, and then replace cosine squared theta plus sine squared theta by 1. And now we have the equation P squared plus Q squared is equal to V RMS I RMS all squared. It looks a lot like the Pythagorean theorem. And in fact, we can show this relationship among P, the real power, Q, the reactive power, and V RMS I RMS, the apparent power. We can show that these can be represented by what's called a power triangle. For an inductive load, the power angle is positive, as is the reactive power, and the power triangle is drawn as shown in the figure. Whereas for a capacitive load, the power angle and the reactive power are both negative, and the power triangle is drawn as shown in the figure in the bottom right corner. Recall that the impedance Z can be expressed in polar form, where it equals the magnitude of Z with a phase angle theta. Or it can be written in rectangular form as R plus Jx, where R is the resistance and X is the reactance of the load. We can plot the impedance in the complex plane, and both the polar and rectangular representations can be derived from the graph. We can see from this graph that the cosine of theta is equal to R over the absolute value of Z, and the sine of theta is equal to X over the absolute value of Z. We can use these equations to rewrite P, the real power, as I squared RMS times R, where R is the real part of the impedance through which the current flows. This is also equal to V R RMS squared over R, where V R RMS is the RMS or effective voltage across the resistance. Because R is always positive and both the effective current and voltage are squared, the real power will never be negative. Similarly, we can rewrite Q, the reactive power, as I RMS X, where X is the imaginary part of the impedance through which the current flows. This is also equal to V X RMS squared over X, where V X RMS is the RMS or effective voltage across the reactance. X is positive for an inductive load and negative for a capacitive load. The complex power, S, is defined to be the real power plus J times the reactive power, or 1/2 V times I star, where V is the phasor voltage across the element for which we're trying to determine the power, and I star is the complex conjugate of the phasor current through the element. We can use all these concepts and expressions to get information about a circuit. Here is an example. We have a voltage source that delivers power to two loads connected in parallel, labeled A and B. Load A has a power factor of 0.5 leading and an apparent power of 10 kilovolt amperes. The power specified for load B is 5 kilowatts, and the power factor is 0.7 lagging. Our goals are to determine the real power and the reactive power delivered to the circuit by the source, along with the power factor associated with the source and the phasor current I through the source. One approach to solving this is to find the real and reactive power associated with each element and add them up to find out what the real and reactive power are for the source. Let's consider load A first. We know that the power factor for the load is 0.5 leading, and the apparent power it uses is 10 kilovolt amperes. Because the power factor is leading, the load is capacitive, which means that the reactive power and the power angle are both negative. We use the power triangle for capacitive elements shown here. The apparent power is V RMS I RMS, and so we can add it to the diagram. The real power for load A is V RMS I RMS times cosine theta sub A. V RMS I RMS is the apparent power which we know, and cosine of theta sub A is the power factor which we also know. So we can obtain the real power, which is 5 kilowatts. We use the equation P sub A squared plus Q sub A squared equals V RMS I RMS all squared to obtain Q sub A. We substitute in the values for P sub A and V RMS I RMS and solve for Q sub A, which is either plus or minus 8.660 kilovolt amperes reactive. We know that the load is capacitive, so we choose minus 8.660 kilovolt amperes reactive. Next, we consider load B. Here we know that the power factor is 0.7 leading and the real power is 5 kilowatts. Since the power factor is leading, we know that load B is inductive, and Q sub B and theta sub B are both positive. We set up a power triangle for an inductive element, putting in the value of P that we already know. We use the power triangle to find theta sub B, which is 45.57 degrees. Now we know both P sub B and theta sub B, which is enough for us to find Q sub B. The value we obtained for Q sub B is positive, which is what we expected given that the load B is an inductive load. To get the total real power delivered by the source, we can add up the power associated with the two loads. We add PA and PB, obtaining the total real power 10 kilowatts. We do the same kind of thing with the reactive power, obtaining the reactive power delivered by the source, which is minus 3.559 volt amperes reactive. The power angle is minus 19.59 degrees. And the power factor, the cosine of the power angle, is 0.9421. The last thing we'd like to find is the phasor current through the source. We can use the expression for complex power to find it. S is equal to the real power, which is 10 kilowatts, plus the reactive power, plus J times the reactive power, minus 3.559 kilovolt amperes reactive, yielding 10 minus J 3.559. This expression equals 1/2 times the phasor voltage times the complex conjugate of the phasor current. We can express the complex power associated with the source in polar notation. And we can recall that the phasor representation of the source voltage is 1414 at an angle of 30 degrees. We can solve for I, and when we do so, we get a phasor current of 15.0 amps at 49.59 degrees.